Thank you, everyone, and welcome to our presentation for Hack PSU. My name is Todd Price. I work as the Corporate Relations Director for Research for the Institute for Computational Data Sciences. What is the Institute for Computational Data Sciences? Well, for those of you who don't know, we have what's called a high-performance computer system on our campus. Today, I brought a couple of my colleagues that are going to talk about what high-performance computing is and what it means for you as a student. Routinely, we have a lot of businesses and research opportunities that come into play, which involve high-performance computing. So to get us started, I'm going to turn it over to Carrie Brown, who's going to be talking about what high-performance computing is.
Thank you, Todd. My name is Carrie Brown, and I am the Research Computing Facilitator at ICDS, which means that I help researchers determine and match them with the resources that best fit their needs. So what is high-performance computing? I really like this definition from inside HPC. It says that high-performance computing, or HPC, generally refers to the practice of aggregating computer power in a way that delivers much higher performance than one could typically get out of a desktop or workstation in order to solve large problems in science, engineering, or business. So the important aspects are this aggregated computing power, right? So if you can do a lot of a lot of science on a single computer, imagine how much more science you can do if you had hundreds or thousands of the computers at your disposal. And that's exactly what we do at ICDS and in other HPC applications, is we take these computers and we network them together to solve these large problems, big data problems, big compute problems, big networking problems in science, engineering, business, and other disciplines. Next slide, please. So this is an example of an HPC cluster. We call this that because, again, it's a cluster of individual computers. That picture on the far left there is one of our racks that contain all these different computers. So each one of those individual rows, or blades as we call them, is an individual computer inside of our cluster. And ROAR, our cluster, has dozens of these racks. So hundreds of computers and thousands of cores. Additionally, you can even scale up even farther and look at more of grid computing. So in that picture on the right is a picture of locations from the Open Science Grid. And these are actually multiple clusters across the nation that have all banded together to solve even bigger problems, to do even larger computing power. Next slide, please. So a really cool example of this is the IceCube GPU Cloudburst. So IceCube is a neutrino observatory located in at the South Pole, and they do high energy astrophysics research. So this particular experiment produces approximately 100 gigabytes worth of data every day. So that's a ton of data to store and analyze. So as part of this experiment, they did a total GPU cloudburst in November 2019, where they utilized all of the available GPU resources on AWS, Microsoft Azure, and Google Cloud over a 2-hour period. So at a peak performance, they were utilizing 51,000 GPUs, and they used over 380 petaflops worth of computing power over 2.5 hours. So it's a really impressive scale of computing that they're doing. Next slide. So at this point, Chuck Pavloski is going to talk a little bit more about HPC specifically at PSU.
So hi, my name is Chuck Pavloski. I'm the ICDS RISE team lead at Penn State, which means I'm a computational scientist. In my case, I'm a domain specialist in meteorology, but I lead a team of other domain specialists and engineers that work with Penn State's researchers and scientists to get their computational needs met and set up on our system, as well as help them tackle some of the more advanced problems that they're trying to do when trying to accomplish their research goals. Now, at Penn State, we recognize that computation and data sciences are completely vital to making our scientific inquiries complete. And we lead a team of engineers and scientists to run on our system where disciplines from all over the university and all the Commonwealth campuses can run and get things done. We are in the business of making research happen at Penn State. Next slide, please. So in that theme, our scholarly community spans a variety of disciplines. For example, the folks here on the left, we have one from Penn State Law, we have someone from geology, we have someone working on materials, as well as working in climate science and materials engineering. Our disciplines that run on our system include things looking for exoplanets and all kinds of climate change roles, as well as peering into the human mind and brain, and actually some genetics. We also do hurricane forecastings and all kinds of other things on our system. And as you can see on the right, our system is considered to be a world-class piece of cyber infrastructure. One other thing that's not mentioned on here that we've been doing that might be a little more familiar is ICDS ROAR has also been used to help do predictions for COVID studies that have been done on campus that have to do with whether or not it's safe or not to return on campus. So our system is not only involved in doing research all over the university and frankly, helping out the world, but a little closer to home when it comes to the COVID crisis that we're working on right now. Next slide. So some of the research that's empowered I've already talked about. Predictive science, in other words, trying to figure out what's going to happen. That does require a lot of computational power. Actually, the slide underneath of it, AI and machine learning, is something that works along the same vein, although it uses different techniques to get to taking data that we have and realizing, hey, what can we learn from the data and how can we predict future offerings of how things are going to change. We also do research on the infrastructure itself. How do we build better and higher performing computer systems? For people that are like yourselves that are about ready to graduate or have aspirations of working in industry, we do computational problems with our partners in industry to try to better the products that they need to get done or whatever advancements they're trying to accomplish working with our researchers. When it comes to future type things that are going to be happening, quantum computing is an up and coming field. Right now, we are working with people on campus that are working on quantum computing coding and materials. And we also have partnerships in industry where we get our access to quantum computers to try to figure out how they are going to work and play in a greater high performance computing system and to make this knowledge available to our researchers. When it comes to things like law and policy and data privacy, for those of you who may be considering jobs that be working at, say, the FBI or the NSA or in defense, we work in those kinds of fields too here, albeit though kind of in helping to develop the more fundamental things that go on when it comes to data privacy and policy. And in fact, our system is currently running, for those of you who are aware of these kinds of things, NIST 800-171 compliance system. Going down to the bottom slide there, we are currently working with folks over in the Center for Immersive Experiences at Penn State to work on things such as advanced visualizations and being able to do things such as immersive experiences. We do have things that we have science that we work with, say, working in social justices and resilience things when it comes to climate change and such. And quite candidly, we are also highly engaged in trying to enhance diversity in the computational and data science fields. And we also work with international partners such as Monash University in Australia to help better our ability to explore the computational and data sciences space. Next slide. So this is a picture of our ROAR system, a different one than what you've seen before. Right now, we have an advanced engineering team that helps maintain and build newer components of this system. So this is not just a 1 or 2 person job. This is a full team of engineers working together to make a system hum the way we need it to hum. The domain experts that we have right now span everything from the biological to the astronomy to meteorology to chemistry to material sciences. We have all kinds of domain experts within the Institute working with scientists and researchers across Penn State. In fact, right now we have over 4,500 users on our system that spans 12 colleges and 80 departments. And we also have an extensive network working with our Commonwealth campuses and scientists all over the state of Pennsylvania. The system that you have here currently has over 34,000 compute cores, physical compute cores. We also have 6,000 virtual cores, which if you are familiar with VMware or VM hosting, we're using similar technologies here that allow us to better utilized cores that may otherwise have wasted cycles. So it's a way for us to get more compute power out of the same hardware, and we're experimenting with those types of systems. Currently, we have over 20 petabytes of aggregate storage between our active and our archive systems. The active system we have is a special type of high performance computing storage known as GPFS, or General Parallel File System. And what that means is that instead of just writing to one hard drive, the way you would typically do on a regular computer with one channel, we have multiple servers that span multiple spindles all at the same time. So we try to get an aggregate read and write capability that is far superior to anything you would have in a desktop system. And in front of this system is a RAM SAN that allows for rapid read and write before it even goes to the spindle. So for folks that are familiar with those kinds of technologies, we are utilizing our high-speed internet interconnect and things like InfiniBand and 40 gigabit Ethernet, along with technologies to read and write in parallel to the system. Right now, we've measured our system to be over 2 petaflops of total peak theoretical performance, which is quite a bit. And we are growing all the time, especially now that we are adding a whole host of GPUs into the mix, which should push us into the 3, 4, and 5 petaflop range very shortly. And as I mentioned before, we have a very secure and compliant system. Next slide, please. So this kind of gives you an idea of what our cyber ecosystem looks like. Keep in mind, the hardware is just one component of a multi-layered system. So in our case, if you look here, the system or compute is just one thing of a whole sphere of our low latency network, the software that's necessary to drive the system. Some of it you may be familiar with, some of it you may not be, because some of it gets into highly technical and specialized things. We have technical services to help them, i.e. the teams that I've mentioned before, the storage system we have, and most importantly are the people. The people are one of the biggest pieces of the puzzle here to make a high performance computer system like ICDS ROR hum. Now, the ICDS ROR system is broken out into 3 different components that we consider our high performance research cloud. The first component is our bare metal system, which we've talked about extensively already. We also have our HPRC, which is our cloud component of HPRC, which is a local virtualized system. That's where the virtual cores come into play. And most importantly, but no, not most importantly, but importantly enough at the same level, would be our ability to burst out to commercial cloud and our government and academic and institute cloud providers. So for example, we can go out to Amazon, or we can go out to Azure, as well as hit a bunch of resources that Carrie will get into later in her section of the slide when she talks about national resources such as Jetstream and Exceed. Next slide. So for you technical geeks out there that like to know about what the basic core counts and all that fun things are and what they look like, here are a variety of our server offerings that we have now. The things that you should take most out of this is that we do things in a way that allow us to have a basic memory allocation for high throughput computing for people that are looking for a more economical way to get their compute done, or an HPC system, all the way up to high memory nodes that have InfiniBand in between the nodes to ensure that the compute and memory from one node talking to another has the lowest latency or time to talk and the highest speed possible. So that way these computers can best behave themselves as one massive machine. You'll notice that we have 40 gigabit Ethernet already as part of the mix on everything we do at a minimum. So even there, it's faster than what you would typically see in a home setup or what you would have even in a small laboratory. Our HPRC system, the one I talked about where we're having virtual cores, that actually has 100 gigabit Ethernet deliberately because we want to make sure that the number of machines that are running on a virtual machine could actually keep up talking to each other and talking to the storage systems that we have. Next slide, please. So how would you access this system if you were running on it? Well, we have a couple of ways that we would have you come on, but the biggest one we have is our web accessible user portal, also known as Open on Demand. Now, Open on Demand is a product that comes from one of our Big Ten partners at Ohio State University. It's one of the few things I like that we got out of Ohio State as a Penn State grad, but that's a whole nother story. The interactive desktop you'll see there on the left is actually what exactly it sounds like. It is a desktop where you log in, and through a web browser, usually an HTML5 compliant one, such as Chrome, you would actually be able to get a virtual desktop that has a GPU running on it at ICDS ROAR to accelerate your graphics. So you could be able to do all kinds of fun visualizations and be able to use anything you would on a normal desktop, but it be remotely. And in this case, you can get all kinds of science done and have it all be done on a system that's computers compliant and backed up. Another part of the portal is this GUI file and Explorer and Editor. So what you can do with that is if you like the drag and drop ways of moving files around, we have a GUI based one. You can access everything you would ever have on ROAR using this drag and drop menu. To next of it, we have our ways that you can fire off Jupyter notebooks and RStudio. We have one for MATLAB as well. We have a whole bunch of other things. So that way, if you have specialty programs that you want to work on, you can actually fire them off independent of a desktop session and have all your storage still be in the same place and have the power of the ROAR supercomputer behind you. And then my favorite way to access things is through just a good old-fashioned SSH shell or command line interface, because that to me is the most fundamental way that you would interact with a computer, is saying, do this, and hopefully it will do that. And so that's another way you can access our system remotely. One thing you typically do when you run on a system like ICDS ROAR is that you submit your jobs into what is known as a batch queue, because you don't want to just sit there and have to watch your stuff run. And you also have to make sure that you are not utilizing resources in a way that could affect other users. So the way we do is we submit these jobs to a queue. This queue is known as our batch scheduler. And what will happen then is you submit your job, you come back later and it's already done. And usually you can set it up to have an email alert you or something to let you know that your computation is finished. It's a great way to make sure you can stack things up and get a whole lot of computing done while sharing this resource with other people. One other thing that we do provide too is strong user support. And as I've mentioned before, we have lots of experts on our team to help you get your computation done. Next slide, please. So I'm going to pass this now to Carrie again, so she could talk to you about some of the things that you can see outside of Penn State when it comes to high performance computing.
Thank you, Chuck. Even as undergraduates, there are a number of ways that you can start to get involved with HPC or affiliated research. One of the first organizations that I would direct you to is this one right here, the Extreme Science and Engineering Discovery Environment. We call this XSEED. They are an NSF-funded organization nationally that provides not only compute and data resources to researchers. So they have really high-scale clusters. They offer cloud computing in the form of Jetstream, like Chuck mentioned, but they also offer educational and professional support. So they have a number of professional networks as well as some trainings that are offered monthly and annually through their programs. You can find out more information at their website, exceed.org. In particular, as students, you can join what's called the Student Champion Program. So Exceed offers this Campus Champions program where individuals at institutions across the US can volunteer to serve as a point of contact and an advocate for researchers wanting to access Exceed services. So we have a number of Exceed champions on the ICDS team, but you can actually join as a student champion. And this is an ongoing program. There are regularly scheduled meetings and a number of different benefits that you get. You get a student allocation on the resources and those sorts of things. Exceed also hosts the PERC conference every July. This is Practice in Education and Advanced Research Computing. This is a great conference if you are interested in HPC and research computing as a whole. Registration for the conference for 2021 will be opening soon. They do offer a student program, which has some student-only opportunities, such as a mentorship program and speed networking, and some special student webinars and trainings. Next slide, please. The other really big conference every year is Supercomputing. That's held in November. This is ACM and IEEE's international conference. It covers HPCs, network storage, analysis, anything having to do with big data and big compute. They have a phenomenal student program, including a student cluster competition and some other aspects. If you volunteer as a student volunteer, they will help cover some of your travel support and provide some other fun perks. Last year, my student received a gift card to buy t-shirts and other fun swag. They're accepting applications for the program through June 28th, so you can learn more about that by visiting the URL there. Also wanted to mention Women in High Performance Computing. This is really kind of a professional organization that's open to women associated with HPC at any stage and aspect of the career. They do offer webinars, trainings, and a mentorship program to specifically support women in HPC. Their URL is there as well. Next slide. So additionally, there's a number of research and educational opportunities, and this is not an exhaustive list by any means. These are just some good places to start. The first is Exceed offers what's called the Empower program, where you'd be paired with a mentor who's doing active research on the Exceed platform. So you can work with them and learn more about how to do these computational workflows. Applications for fall 2021 are due in June, and they do offer a small stipend for this program. The other one I want to mention is actually the one on the bottom. This is Cyberinfrastructure Research for Social Change. This is also a research opportunity specifically for undergraduates. It's a 9-week program where you would be paired with researchers at the University of Texas at Austin. This also pays a stipend, and applications for this are accepted between November and March. So unfortunately, the period for 2021 is closed, but you can apply for 2022 starting in November of this year. And finally, the Open Science Grid that we saw the picture of previously does a 1 to 2 week long user school, which focuses on how to use the Open Science Grid and what high throughput computing is. And they start accepting applications around March or April. They haven't announced it yet for this year, but they should shortly. So if you're interested in that as well, the link is there too. Next slide. And finally, you can get involved with HPC just while you're here still at Penn State. ICDS offers a number of new user trainings. We announce interdisciplinary research opportunities as they arise, and we have a number of new events such as symposia and different talks. So to learn more about those, I definitely recommend that you visit our website at icds.psu.edu and sign up for our mailing list. If you have any questions or want to reach out to us for more information about any of this, feel free to do so at the email listed there, iask@ics.psu.edu. Thank you.